Okay, in this video we're going to have a look at graphs of derivative functions. Okay, so we say that a function is what we call strictly increasing over an interval if the derivative or gradient is always greater than or equal to 0 on that interval. Okay, and similarly, if the derivative or gradient is always less than or equal to 0 on the interval, then we say it is strictly decreasing for that interval. Okay, so we've got an example here, okay, using some of this information. So for the graph shown, state when f dash of x is greater than 0, f dash of x is less than 0, and f of x equals 0. Okay, so we're looking for when we've got these positive ones. Okay, so my analogy is if you're walking across a page left to right, okay, if you're walking uphill, okay, the gradient is positive. If you're walking downhill, the gradient is negative. Okay, so if we're looking at that, okay, then for when f dash of x is greater than 0, positive, well, we can say it's for all x values, okay, less than 2, okay, because we're here, okay, but also going to be positive, okay, for x values greater than 5, okay, because it's going to be walking uphill here and uphill there. So we can also see then that our gradient is going to be less than 0 or negative when we're walking downhill, which is when we've got x values between 2 and 5. Okay, and our points where our gradient, okay, are 0, okay, they're our turning points. So our turning points are the points where we're always going to have gradient equals 0. They're known as stationary points, and we can actually have one as well for cubic functions. Okay, another stationary point, okay, where our gradient is 0 there. Okay, so it's these points, so it's going to be when x equals 2 or 5. We've got a little bit more that we can do with this though. So if we're given a function, okay, what we can do is actually sketch the derivative function, okay, without actually knowing what the function is. So we want to, and that's what we want to do here. So we've got these two functions, and we want to sketch some derivative functions. So what we can see here is that our gradient is negative, okay, to start off with. Then there's a point where it's 0, here at 1, right? Then it's positive after that. So what that means for our gradient function is we know it's 0 at this point. Okay, it's a negative, which means we're going to be below the x-axis. If you think of this as negative and this is positive, okay, so it's going to be negative when we're less than that, okay, and it's going to be positive when we're more than that. Okay, so we'd end up with something that looks like this, some sort of linear function. So this looks like it's some sort of quadratic, okay, which would make sense then, because our derivative of a quadratic becomes a linear function, so it makes sense that something like that. Similarly here, we can see that we've got 2 points where our derivative, where our gradient is equal to 0. Okay, remember this is positive, this is negative. Okay, so we can see here for this first component, okay, our gradient is positive, so we know we're going to be up here. In the middle section, it's negative, so it's going to be down there. Over here, we become positive again. So you can see we're going to do something going through like this. Okay, and again, this makes sense because our black line here, that function, was in the form of x cubed. Okay, some sort of cubic. We take the derivative of that, okay, we get back to a quadratic. Okay, so it makes sense that it's some sort of shape like this. Okay, there's one last little part that we can talk about. Okay, I'll go a little bit further than what they do in the textbook for this section because they kind of just do a little introduction, but can really be taken a little bit further here, which is looking at the angles of functions at the x-axis. So when we intercept the x-axis, we can look at the angle that is formed there. So the angle theta that a function makes at the positive x-axis is found using inverse tan of m equals theta, where m is the gradient of the function at the x-intercept. Okay, we've got an example of how this works too. So we've got f of x equals x squared take 1, and we know, and we're told that it has x-intercepts at x equals -1 and x equals +1. Find the angles associated with the x-intercepts. Okay, so what we're saying, okay, is it's going to look something like this, and we know this is at 1 and this is at -1. Okay, and we're wanting to find the angles. Okay, and that's to the positive x-axis. So we're looking at here, we want this angle. For this one, we actually want that angle. Well, there's a nice symmetry that works in here. Okay, so what we need, of course, is our gradient at those values. So first of all, we need to find our derivative. So f dash of x, well, for x squared take 1, is simply going to be 2x. We're told that our intercepts are at 1 and -1, so f dash of 1 is going to equal 2, and f dash of -1 is going to equal -2. Simply putting in x equals 1 and x equals -1 into our gradient function. Then we can use this function. Okay, so for here, we'll go inverse tan, okay, of our gradient, which was 2, is going to equal our angle. Okay, and when we do that, we find that our angle is 63.43 degrees. Okay, and that's in here. Okay, for this one, when we do inverse tan of -2 equals theta, okay, we actually find that theta is going to also give us a very similar value, but actually gives us -63.43, and we need to interpret that, okay, and that's really saying that you know how to think of it as that's our angle over here, or the angle down there. Either way, it's not actually the one that we want. Okay, what we do want though is 180 minus our 63.43. Because we can see that that's going to be bigger than 90 degrees. So we're going to be 116.57 degrees. Okay, so this takes you a little bit further than what the textbook does. There's not a crazy big leap in thinking from what the textbook talks about. So hopefully that will help you get through the questions on this section.